engineering optimization platforms are an important tool for any engineer. Now, we're going to work today on solving linear programming, quadratic, nonlinear, mixed integer, linear programming, and mixed integer nonlinear programming in Python, both with SciPy and also with Gecko package. So we're going to go through some simple examples and then also let you try it out on some of these exercises that are right here. I'll post this link. You can come here to the Google Colab link and just run through your web browser without installing anything. Or you can come back here and go to the GitHub link, and that will bring you to a place where you can download this Jupyter Notebook and follow along. So we're just going to start with this Jupyter Notebook right here. And I'm going to go through the very first thing that you'll need is just to go ahead and pip install the package that you'll need for this exercise, which is Gecko. Now, once you've installed this, or if it's already installed, you can comment it out. Okay, so that's already installed, and then you can restart the kernel, for example, if you need to. Okay, that's only if it's installed for the first time. You'll need to reinstall that or restart the kernel. Okay, so I'm going to come down here to linear programming. So the very first thing we'll see with linear programming is that we're going to try to minimize, okay, c times x subject to, and then we're going to have something like a1 times x equals 0, a2, actually I'll put a b there, b1, a2 times x is less than or equal to b2. So this is a standard form that's often used for linear programming, and then we just fit things into these matrices or vectors, for our constants or parameters, and then we let the problem solve it. So we have, in this case, a company manufactures two products, in this case G and H, and it has two resources, X and Y, available. Now each unit of G requires 3 units of resource X and 8 units of resource Y, and each unit of product H requires 6 units of resource X and 4 units of resource Y. The company has a maximum of 30 units of resource X and 44 units of resource Y. The company wants to maximize profits. It can sell G for $100 per unit and H for $125 per unit. Okay, so here is our linear programming problem that describes this problem. We're going to maximize our profit, which is 100 per unit times the number of units G, plus 125 times the number of units H. Okay, here's our resource constraint for X, and then we also have a resource constraint. That's like our raw materials for Y. And then we know that G and H have to be greater than or equal to 0. So let's start with SciPy linear programming. Here's our standard form right here. Instead of A1 and B1, A2 and B2, they use this A upper bound and B upper bound. Or so you can just fit it into these forms and then solve it. Okay, so here is SciPy. We're going to import linprog, and there's our C matrix. Okay, we're going to convert it to a minimization. So we have to multiply by negative to get it into the minimization form. And then there's our A value, and there's our B value. And we'll have a bound from 0 to none for G and H. And then our result is going to be this linear program, and there's C, and there's A upper bound equals A. B upper bound equals B, and then there are bounds for G and H. Our method will use the highs package as a solver. And now let's go ahead and just print the solution. So it'll print out x0 and x1, which are G and H. And then we'll look at the maximum profit. Okay, so I'm going to run this, and you can see there's our optimal solution right here, G and H, 4 units of G and 3 units of H. And there's our maximum profit as well. Let's solve this same thing with Gecko. All right, import Gecko, create our model, G and H. We're going to create an array of values as variables. And we'll have that array be length 2. and we'll have a lower bound of 0 for each of those. Now we're going to try to maximize 100 times g plus 125 times h. And then we have an equation, 3 times g plus 6 times h is less than or equal to 30. And then the same thing for resource y, that's less than 44. We'll solve it, and then likewise print our solution. We're going to print g and h and get the values of both of those. And we'll just limit it to 2 decimal places. And then also print our maximum profit. And there's our objective function value. Again, we're going to convert it back to maximize by printing the negative of that. Okay, also just 2 decimal places for that. Okay, I'm going to solve this, and it gave me the same solution. So between the two, Gecko is just a little bit easier to understand. And this one is likewise fairly easy. You just have to put it into matrix form. Okay, let's go on to an activity now where we're going to solve this problem, the linear programming problem, using either Gecko or SciPy to solve this and print the results y and x. So here I have a graphic on the left here that just shows the feasible region. Okay, so those are all potential solutions right here in, so these are feasible potential solutions. Now in linear programming, one of the things that we always know is that we're going to be at the vertex, at the intersection of some of these constraints. Okay, and we can see the contour lines here for our objective. We're going to be maximizing x plus y. All right, so you can see x here and y over here. And so we're going to try to move as far up this way as we can within that feasible region. Now you'll see here the solution is 4, the solution is 4 right here for our objective function, but right here the solution is 4.5. So that's our best solution right there. I'll just make that yellow right there. There's our 4.5, the optimal. But let's set this up and solve it with Python. Okay, I'm going to do that with Gecko. Now, if you switch it to remote equals false, it doesn't solve on a remote server. It solves locally on your computer. We have x and y. I'll create an array with 2 values. They're going to have a lower bound of 0. I'll create my equations. Now, here are all of my equations. I'm just going to include these as a list. Okay, and then I have maximize x plus y, and then I'll solve it. And there are my optimal values. I'll just assign to different variables and then print those out along with the objective function. Okay, so it came up with the optimal solution as we had already found from our chart. This is x is equal to 3, and then y. Y is equal to 1.5. And the optimal, okay, the optimal objective function is there. It's the 4.5. Okay, you'll notice that it's not necessarily round numbers there. It's because we have certain tolerances of accuracy, and so it doesn't iterate forever to get just that very last decimal place of accuracy. It stops after a certain period of time. 1 times 10 to the minus 6 or 1 times 10 to the minus 8 is typical for convergence. Okay, so there we have our plot. Now we can also visualize the solution. If you want to recreate this plot, I'm not going to go through this code with you, but it's there if you would like it. I'm just going to create a mesh grid, show an image with all of the feasible region, plot my constraints, create some plots with those lines on it, and then mark the points that could be potential feasible optimal solutions at the vertices, and then put my contours and then my optimal point. I went through that very fast, but if we run it, then the thing that we'll see is it found this optimal solution right here, and you can see the rest of the plot that I'd showed you earlier. So let's go on to quadratic programming now. So quadratic programming is a little bit different. The objective function is going to change here. Instead of c times x only, okay, or we could go, p times x, we're going to add 1/2 and then x transpose times q times x. Okay, so we're going to add this additional quadratic objective function. Now you can also have quadratic program quadratic constraints. So that means that you have an objective function. Okay, that's going to be our objective function right here. But you could also have a quadratic constraint down below. Okay, maybe that's not q, maybe that's, let's call it r. And maybe that's equal to value b3, something like that. So we can put these quadratic constraints down below as well, and then we just call it QP, QC, quadratic constraints. So quadratic programming with quadratic constraints. So there are many good solvers out there that can solve, this type of problem. Clean this up just a little bit. I'll put a my R here. Okay, so let's go ahead and set this up and solve it. Okay, just a simple quadratic programming problem within Python. Now, we're going to have some problem data. I'll put in my Q matrix, my P vector. This is going to be a problem where a car manufacturer wants to minimize the weight of a car while maintaining a minimum strength requirement. The weight of the car is modeled as a quadratic function of the thickness of the car frame components. The strength of the car is modeled as a linear function of the thickness of the car frame components. The manufacturer wants to minimize the weight of the car while maintaining a minimum strength requirement. So this is our problem right here. All right, so let's go ahead and put these in there. I'll just go ahead and do the rest of these. There's our strength constraints for G and H. There's our initial guess. Okay, so if I run this, it'll feed in those parameters and store them locally. Now let's go ahead and solve this with SciPy. And we're going to use the minimize function from SciPy optimize. So I'll import the minimize function, and then I'll need to define an objective function. And I'll return 0.5. Let's see if I can come up here and just show that to you. Okay, so here's our objective function. Okay, it's going to be x, and then use the @ symbol there to do a dot product. Okay, and then we have plus p times the dot product p times x. So this is going to return a scalar value, a single value from that objective function. We're also going to define our minimize function, and we'll put our objective function there with our initial guess. We also have some constraints, and this is going to be an inequality function. And so let's go ahead and define that. Okay, so here's our inequality. I put everything onto one side of the equation. Okay, so you can see that's g of x, g times x is greater than or equal to h. So we got to have it in terms of in terms of SciPy optimize. We'll just fit this constraint, this one right here, into a g of x is greater than 0 form. Okay, so we'll fit that into that form for SciPy optimize minimize because it solves general nonlinear problems. Okay, there's our constraint. And let's go ahead and put in some bounds as well. We want to go between 0 and 10 for our bounds, and I'll add that as an argument. And then let's also put in a method, the successive linear, this is a SQP, sequential quadratic programming problem, with this algorithm SLSQP. Okay, I'll also put in maximum iterations of 1,000. I don't think we'll need it here, but you can always change the number of iterations. Okay, there's our optimal solution. So when we solve it, we'll see that the optimal solution is 2 and 1, and there's our minimum weight. Okay, so we've met all the requirements, and we also have this minimum weight. All right, so you can see you can define your objective function, your constraints, and bounds on your variables. Okay, let's go on to Gecko for quadratic programming. I'll create a new Gecko model, remote fault, so it solves locally. And then I'll have my variable here. Okay, so x0 and x1. And I'll have the lower and upper bounds on those. And I'll minimize this, 0.5 times x, and then qx, so x transpose. You don't necessarily need the transpose in here. It'll figure that out. Okay, so plus p at x. So there's the dot product of p and x. And then also have gx, and then create my equations here. So I need to go through and add each row of this individually. So there's gxi greater than or equal to hi for I in range length h. Okay, and I'll solve it and then print my solution. Okay, it gave me the same solution. Again, I just have a solver tolerance because these are numerical optimization methods. Okay, so here it is in Gecko, and there it is in SciPy. Okay, let's go on to a nonlinear. Okay, nonlinear programming. I'm going to just write this out. We're going to minimize. We're going to minimize f of x subject to, and then we'll have g of x equals 0, and then h of x greater than or equal to 0, or just greater than 0. The two are equivalent. So let's go ahead and solve a problem here with, we're going to go on to nonlinear next. Actually, we have one exercise here. First of all, with the quadratic programming, just an exercise for you to try this out on your own. It's the same as before, except we just added a quadratic objective function here. So go ahead and try that yourself, and then we'll move on to the nonlinear. Okay, solve the QP. A lot of this is going to be a repeat from what you saw before. So I'm going to go a little bit fast through it. Okay, there are all my equations. And then I'm just going to change maximize to that new quadratic programming problem. And then I'll solve it, and then get the results, and then print x and y, and my objective function as well. So here I can see that it's 1 and 2, and you can see the objective value here. So let's go ahead and visualize this with QP objective and constraints. Okay, I'm going to go very fast through this. Again, it's just a contour plot that helps us visualize the quadratic programming solution. Now, the thing that's different here is that I now have, instead of a linear objective, I can see I have a quadratic objective. And so you can see the purple, blue, green, light green, yellow, and you can see the value of that objective. Now I'm trying to maximize this to give the highest value. And the one that it picked out, you can see it was x is 1 and y is 2 with an objective of 4.5. So x1, y2, and so it's up here on the this upper vertice that you can see. That's a 4.5 objective, and so that's going to be your highest objective up there at 1, 2. Okay, so there's our quadratic programming exercise. Let's go on to nonlinear programming now. So that fits into this form that I showed over here. So f of x, I'm just a function of all my x values. Those are my decision variables. I'm going to be subject to equality or inequality constraints. And in this case, it gives us, it'll give us this, here we have an inequality constraint, okay, the product of all the values, and the sum of the squares of the values is equal to 40. Now, I also say that my x has to go between 1 and 5, and there's my initial guess. All right, so let's go ahead and just solve this with SciPy, first of all. So we did that with the quadratic programming problem already. We'll get a solution we're going to minimize with an objective. So let's define our objective function first. there's our objective, which you can see right there at the top. And we'll have a constraint. We have to put everything onto one side of the equation. So the product minus 25 is greater than or equal to 0. And let's go do our second one. There's the sum of the squares. So I just did that in a loop. I'm going to put in here method as SLSQP, and I'll put in my initial guess x0. And then let's go ahead and just put in my bounds. These are going to be between 1 and 5 for each of those. And then also my constraint. I have an inequality constraint. There's constraint 1, and constraint 2 is going to be an equality constraint. So let's put those together as a list and put it there as one of my inputs to my optimization for minimize. All right, I'll get my solution and then print my objective and my solution. So when I solve it, I'll see there are my x values that are optimal, and there's my objective function that's also optimal. Okay, let's solve this same thing with Gecko now. So Gecko, I'm going to have my variables that are defined between 1 and 5, and I gave it all initial guess value of 1. So let's go ahead and split those out to x1 to x4, and I'll change the initial guess values for x2 and x3 to be equal to 5. Now I'll have my product of all my values is equal to 25, and I could substitute this. I could substitute this with a NumPy function like mp.product of x. Okay, so that'd be another way of doing it if you wanted to. I'll leave it here as just the x1 times x2 times x3 times x4 is greater than or equal to 25. There's my sum of the squares is equal to 40. I'll minimize that objective function and then solve it. Let's go ahead and print the solution. So same solution with Gecko. All right, so let's go on to solving a nonlinear programming problem. Here's some linear constraints, but we have a nonlinear objective here. It's not a quadratic objective. It'll be a full nonlinear objective. So let's solve this with Gecko. I'll have x and y. I'll have a lower bound of 2. I want to minimize that objective function. There are my equations. And I'll also have display equals false, and then get my optimal values, and then print my solution. So you'll notice here I converted these right here into just simple bounds. Okay, when I defined it between 1 and 3, but this one was different. So I just changed the lower bound to 2. Okay, there's my optimal solution. Now let's go ahead and just visualize this with because I have just 2 variables, it's easy to visualize it with a contour plot. You don't need to necessarily know how to do this again, just if you want to run it to verify that you got the right solution. Okay, so it said 2.5 and 2 with an objective function of 0.25. All right, so here is the gray area is my feasible solution area. Now, if I'm trying to minimize, then my minimum is going to be right here on the very right of the very far right lower gray part, the intersection between the black dashed line and the black solid line. Okay, and then if I'm trying to maximize, it looks like it's going to be in the upper, maybe the upper right of that gray area. So if I'm maximizing instead, so let's go ahead and just try that. Okay, I'll just try to maximize it. Okay, so it gave me 1.66 and y equals 3. So that looks like the correct solution right up there at the top. Okay, so let's go on to now mixed integer linear programming. So this is similar to what we did before with linear programming. So I'm going to minimize CX subject to, and then I'm going to have my equality constraints and my, I'll do a2 times x less than, or you could do greater than, b2. But then I could say that some of my x are integer. okay, are going to be integer values. So that would be 1, 2, 3, etc. If it's binary, then it says it has to be 0, 1. Or I could also have, okay, so that's integer, binary, or I could just have general discrete. So that could be something like 0.1, 0.5, 1, you know, on down. So you could say, I want you to select from this set of unique values, but it can't be in between those. So that might be the size of a pipe. That might be, some other types of, discrete constraints there. So you can have integer, binary, or discrete. But let's go ahead and just solve this just as integer variables first. I'm going to use linprog. Now, you can also use the MILP function that's also in SciPy Optimize, but I'm just going to use linprog because it allows us to keep the same interface but just define integrality. Okay, so same thing as before, linear programming problem that you're already used to solving, and there are our bounds, but the final thing I'm going to add is this integrality. So if it's 0, then it means it's continuous. If it's 1, it means it has to be an integer value. And so let's go ahead and just print the solution to this. And so you can see that it found an integer optimal solution and the objective function there. The objective function doesn't necessarily have to be an integer. We just specified that our decision variables had to be integers. Okay, so that's how we solve a mixed integer linear programming problem with SciPy Optimize, the linprog. Okay, now we can also do that with Gecko. The way we do that is we just specify integer equals true for our variables. Then we'll minimize c times x, and then put in our a constraints as well, just like we did before. And then we'll solve. Now we need to switch to solver APOpt solver because it was able to solve mixed integer problems. You can also solve mixed integer nonlinear programming problems, but we'll just use this to also solve a mixed integer linear programming problem. Okay, and we see it came up with the same solution as before. Let's go ahead and solve now our same one that we had done before. And if you remember, this one came up with a solution that was not at an integer value. Okay, so that was y of 1.5. And if we just look at this, we can see that we have integer values that are going to be, let me go and do a different color here. There's one right here. Here's another one. And then a final one that we want to pay attention to is going to be right here as well. Those actually have all the same objective. So there are 3 solutions to this when they are integer, when you specify that they need to be integers. Okay, the objective function is going to be 4. It's going to be along that line. All right, let's go ahead and solve this with Gecko. Okay, and we'll just put in all of our constraints as before and maximize, and we'll get our optimal values. So when we solve this, you'll see that it is solving at a continuous value. So we'll have to add in the M options and then solver and switch that over to solver 1. Okay, and then you can see it comes up with one of the integer solutions there. All right, so here we are going to go on to now mixed integer nonlinear programming. So just like we'd solved before with this nonlinear programming problem, but now we're going to also add these integer, discrete, or binary values. And then we're going to follow up with an exercise on how to fold paper to maximize the volume of a box. Okay, so let's go ahead and solve this just like we've done before. We're going to create some integer values. Okay, this is going to be x1 and x2. We'll create different bounds for those. And we'll also create a continuous variable x3. Okay, there's our objective function to minimize, an inequality constraint, and also our solver. Okay, there are the values. Okay, we can see that these are going to be integer values, and then this final one right here is continuous. Okay, let's go and do the discrete one. Maybe we want to select one from this list right here. So let's go ahead and just define this problem again. Okay, but we're going to create a special ordered set. So x2 is m.sos1. That's special ordered set, first type. So basically you can have just one of those values. sos2 is you could have two of those values. It's a different form for that, but let's go ahead and just create this 0.5, 1.15, 2.6, 5.2. Also have our continuous variable in there as well. And then there's our inequality constraint and our objective function. We'll solve this with the APOP solver and then print our values. Okay, so of those, it chose this 5.2 for x2. You can see that was our special ordered set. It allowed it to choose one of those four values. This first one, x1, is still an integer. Okay, so there's our 10. And then our final one, x3, that's still a continuous variable. Okay, so there's our optimal solution. Okay, for the final one, we're going to have this activity to solve a mixed integer nonlinear programming problem. We have a piece of paper. Okay, it's 8.5 by 11 inches. All right. And if you're in Europe or another country that uses a different size, you can modify this. Basically, what we're going to do is just restrict the volume of the box to maximize it, but we'll need to restrict the height of it to integer values. Okay, whether that's inches or centimeters. Okay, so you have here a box folding template. Okay, you can print that out if you'd like. Also, there's some additional information here on optimization. If you want to go through these questions, it'll help you show you some of the code and help you understand the derivation of this model as well. Okay, and then just here's what is the cutout size x. It maximizes the volume. This would be for the continuous solution, so our correct one is right here. But let's just come back here. Okay, so starting with the continuous solution, let's restrict the height to inch values, so integer inch values. All right, so let's go ahead and create this. There's our paper width and length, and then our decision variable is this x value up there. So how long that the height is going to be for our box as we fold it up. Okay, there's our box width. I'm going to create an intermediate variable. Now I use these in Gecko to help me simplify the problem description. All right, and then I'll have minus 2x. So my box width is going to be this width of the paper minus 2 times x. All right, and then the box length is similarly going to be the paper length minus 2 times x. And then my box height is going to be x. And my volume is going to be the width times the length times the height. And then I'll have a lower constraint for box width with tabs. Okay, so if you had tabs on it to fold over, you need to include a little bit of extra space there, but we don't. Box width has to be greater than 0. Box length is greater than 0. And then volume, I'll just say that's greater than 0.01. Okay, we want to maximize the volume. I'll use my solver and then say display equals false. So do not print out the solver solution. And there I'll have my width and my length and my height. Okay, and there's my volume. Now you'll notice here, this is the continuous solution. So it's going to come up with a volume of 66. Okay, so there's my volume right here. I'll just copy that over here. There's my continuous volume. And then let's go ahead and restrict this to integer values now. Okay, so integer equals true. If we solve it again, we'll see that the height came out to be an integer value. And then you can see that the length as well. The length is an integer value. But the width is not, because that was, you got minus 2x, okay? So the x is equal to 2, so you're subtracting 4. All right, so there's my width, length, and height of the box. And then you can see there's my new volume right here. I'm going to copy this over. Okay, so my volume difference, okay, is going to be this amount. Okay, so I'm losing 3 cubic inches in my box by enforcing that I have this integer value. Now you'll always see that as you add additional constraints to a problem. If it's non-convex, then this doesn't necessarily hold true, but if it's convex, if there's just one local minimum, then adding additional constraints will keep the objective function the same or make it worse. Okay, so it's going to make it just a little bit worse, only by 3 cubic inches though. All right, so here's my solution. So now if you take your piece of paper and then based on this, go ahead and just mark out, how much x is there. And then you can just fold it on the diagonal here. Okay. Fold it on the straight edge. Oh, I'm not doing a very good job of this. Okay. And then fold it on the length, width, and edge. And then this will then just fold up nicely. I'm not doing a very good job of showing this, but you can just fold it into a box just with this little tab that's there that's just kind of creased over. Okay. And you can put some tape on it if you want to. Here's my final box right here that I've already folded up that maximizes the volume of the box given that decision variable of x. Okay, well, I hope you've enjoyed this exercise. We've gone through quite a bit here. We went through linear programming, quadratic, nonlinear, mixed integer linear, and mixed integer nonlinear programming, both with SciPy and with Gecko. You'll notice here at the end, we didn't use SciPy to solve the mixed integer nonlinear programming. I believe a version of that is going to be coming out in a future version of SciPy. It isn't here yet, but it might be there shortly. There are also many other great packages that you can use to solve these types of problems. Here in the optimization course overview, if you come to optimization software, you'll see a review paper and a presentation that I gave on data-driven modeling and also equation-oriented modeling as well. So many great software packages that can be used to help simplify the expression, the mathematical expression of some of these types of problems, and help you do it with a modeling platform that can give information to the solvers like automatic differentiation to obtain the derivatives, so it can solve very efficiently, especially for larger or more complex problems. Also, when you're dealing with anything larger than these tutorial problems, it's nice to have a modeling platform to just simplify the description of the problem. Well, I hope you've enjoyed these tutorials, and I'd love to hear your comments and suggestions for future content as well.